This is the makeup lecture for PGE301 for some of the time we missed due to our snow and ice days. And it's going to have a little bit of repeat of what I covered in class this week, but I'm starting at the beginning of the energy and environment section. So to talk about the energy and environment, a great example to show how this is dealt with is Texas. So here are a couple pictures from Texas. On the right, we have a farm field, ranch field with some pump jacks and indicating oil and gas production as well as windmills. So Texas farmers and ranchers are using their land for kind of an all-of-the-above energy strategy. And so that's basically epitomizes the production, make the best of the resources you have attitude in Texas. On the left is a flare, and I'm going to turn the video on and you can hear how loud the flare is. I'm probably maybe 500 to 1,000 feet away from it, and it's really quite remarkable how loud it is and how big it is. This flare boom is something on the order of 80 to 100 feet tall. Okay, so the reason why the flare is a symbol of kind of the environmental problems in the fossil fuel business is twofold. One is it's burning natural gas, which is a resource that could be put in a pipeline and sent to market to be an energy resource for the country. And fossil fuels are a finite resource, so this is a waste of a finite energy resource. Secondly, either burning or venting methane gas creates greenhouse gases, which have an impact on climate. There's a lot of debate about the degree to which we need to worry about that, but this is an example of flaring, of CO2 emissions and maybe a little bit of methane if the flare isn't burning 100% of the gas. These are emissions that have no purpose other than to sell oil. So they're not being used as energy resources for a productive purpose. They're being used as a financial tool in order to be able to sell oil and gas. Now, one thing that's important to say about flaring is it is required to flare some of the time. Okay, basically, it's a safety operation. When you're running collection facilities or other things like that, there might be an upset in the facility and you have to keep the gas moving. You can't just stop it from coming in, and so if its outlet has been blocked in some fashion or something like that, you need to be able to dispose of the gas in a safe way. And the safe way is to not just vent methane, which could be an explosion hazard. You want to burn it. Okay. So anyway, so this is a little bit pictures about energy and environment. This is kind of the poster. This is the poster child of the environmental movement, particularly before COVID. Greta Thunberg, basically talking about we should be getting off fossil fuels. So let's talk a little bit about what the arguments are on that side of the discussion, and we'll continue to have discussions about the positive aspects of fossil fuels as well as of environmental impact. And as in all things, basically, in society and broader life, there are trade-offs. So if we didn't have fossil fuels, we wouldn't have emissions, but we also wouldn't have the energy we need. And having appropriate energy, addressing energy poverty, those are extremely important aspects of the energy business that can't just be washed away by saying we don't want CO2 emissions. So if we look at world consumption, this is from 1965 to 2020. This is data from the Energy Institute data set, which used to be the BP data set. The consumption goes up to almost 200 exajoules. This is per year. And basically what you want you to see here is we've got oil, coal, gas. Oil, coal, and gas are the dominant sources of energy for consumption of the world. And we are continuing to increase in our consumption as humans seek a better way of life. Down here, hydro, you can see worldwide is growing. In the United States, it's not growing. And nuclear is kind of plateaued. There's been a lot of safety and environmental issues that have come up in nuclear that have caused people or caused governments to move away from nuclear. A lot of people are trying to reverse that. They think that the reaction to some of the environmental events like the Fukushima nuclear reactor meltdown because of an earthquake tsunami, some people think that's an overreaction to basically move away from nuclear. And nuclear is a excellent baseload low emissions resource. Then you can see at the bottom, the green curve here is renewables. You can see renewables basically in the form of non-hydro options, which are predominantly wind and solar, really didn't become anything in the world until about 2000, started to rise, and now we can see we're up to a little bit over 20 exajoules compared to the 200 exajoules the world is using every year from petroleum. So renewables in the form of wind and solar, non-hydro renewables, are still a very small fraction of our resource. Now, why are fossil fuels consumption an issue for some, for the environmental side of the discussion here? And it's the 35 gigatons of CO2 per year that fossil fuel consumption contributes to the atmosphere. And we'll talk a little bit about some of the climate change outcomes that are attributed to that CO2 emission. The other thing I want to talk about is the Paris meeting called COP21, where the United States signed on to an agreement to reduce fossil fuel emissions. We'll talk about it in detail in a little minute. So this is the agreement that we used to be a signatory to when Trump became president the first time. We left the agreement when Biden came in. We signed back on. Now that Trump's back in, we're signing back off. But to me, this is kind of the reference event where countries first got together and really made a commitment. All countries, or most countries in the world, made a commitment to reducing emissions. So I want to talk a little bit about that. And this actually, I had the pleasure of attending this, mainly because of my wife, Dr. Hillary Olson, was working the carbon capture and storage booth at the convention at the COP21, the technical convention associated with COP21. Here in the middle is the United States pavilion here. So they had a lot of activity there talking about things in the United States going on related to emissions and climate change. So what happened at the Paris Agreement? So 170 countries pledged to reduce greenhouse gas emissions, to limit global temperature rise by 2100. So they're trying to limit how much temperature will rise when we go out to year 2100, and they wanted to keep that rise to below 2 degrees C as compared to pre-industrial levels, which is back in the 1800s. The United States and Europe made pledges based on reference past peak emissions and made reduction pledges out to United States made a pledge what we'd do by 2025, Europe by 2030. China, so we'll talk about those in detail in a second. China pledged to reduce or to peak their emissions by 2030, and India pledged to reduce their emissions intensity. So that means for every unit of energy that India burns, they were going to reduce the amount of CO2 it emitted. That doesn't mean that their emissions would be reduced because their energy consumption is increasing rapidly. So they're just trying to mitigate some of that increase. So China is saying they'll peak. India is saying they'll mitigate their increase. The US and Europe pledged to reduce their emissions. So here's a chart again from this EI Energy Institute Statistical Review of World Energy showing data from China, and this is population in parentheses, China, the United States, all of Europe, and India. And so we go from 1965 to 2023. And so what we have that you can see here, China is by far the biggest emitter, but really their emissions took off at an unbelievable rate in 2000. And that was when really they had their economic revolution, and that was all powered by coal-fired electricity. And so if we move this down to look at their growth, so if China had started at 0 in year 2000, they would have been, well, basically what this shows, if you look at the U.S. consumption here in blue, China added almost 1.5 U.S. consumptions. I mean, in reference to our current day emissions, this is in 25 years, they added 1.5 times the U.S. total emissions to the CO2 budget. Okay, so what this shows is as large undeveloped countries seek a better way of life, they're emitting huge amounts of CO2. Okay, so what you could ask, what justifies that kind of growth? And before I talk about that in detail, let me just talk a little bit more about the other curves here. So here's the United States. You can see back in 1965, we were below 4 gigatons per year. We hit 6 gigatons per year of CO2 emissions related to energy in 2005, almost hit that, and now we're declining. Europe used to be almost exactly along the lines of the United States. This is the fall of the Soviet Union, so some additional countries were added to Europe. And then you can see like Europe plateaued in the 80s and has been pretty flat until basically 2005. They started to work much harder on reducing emissions. And then India, well, China, as we talked about, China was rising slowly. Well, really, this is fairly rapidly, but then just really took off in year 2000. India's, you could say, maybe something on the order of 20 or 25 years behind China for emissions. Okay, so what could justify emissions growth? A lot of people want to blame countries like China for their emissions. Well, they have a huge population. Now, their population growth isn't reflected in this. This is a much faster increase in emissions than their population growth, but population growth could increase emissions from a country. A historical lack of emissions of a particular country could make them feel like they're free to emit. The reason why countries would have a historical lack of emissions would be that their economy is not so developed, so they didn't use so much energy. And you can see here, while China and India were very low back in the 60s and 70s, the United States and Europe were here the top emitters in the world, basically building up a store of CO2 in the atmosphere. So the question is it fair to say that China can't have some of that freedom to emit in order to advance their economy? And the reason to advance your economy is to improve standard of living. We've talked about this a fair amount, but if we look at, for instance, the per capita income of a citizen of China in year 2000 was approximately $940 per year. At the end of this rise in emissions, which is their essentially economic miracle powered by the energy from coal, they had increased the per capita income by more than a factor of 12. It's an incredible improvement in standard of living for the typical Chinese citizen, and all basically underpinned by the energy coming from coal. If you look at the United States over the same time period, we started out with an income significantly greater than China, like 36 times, or even more than 36 times the per capita income. And we've declined since 2005 in emissions, but our income has doubled. So the United States is actually increasing its wealth by reducing its emissions from energy consumption. You look at Europe. Europe is basically per capita income half of the United States. So Europeans don't have a similar energy-intensive lifestyle that the United States does, which reflects the standard of living. And by the end of this time period, Europe had also increased, more than doubled their per capita income while declining in emissions. And so we'd like, the general trend would be to hope that all countries could do that. But if you see this, China has a long way to go to catch up to the United States income. So present day, typical U.S. income is still almost 8 times a typical Chinese person's income. We look at India. India is way behind China. So you can see the curves here are CO2 emissions, but you can see they kind of reflect the income as well. So typical Chinese income, or per capita Chinese income in 2000 was twice what it was in India. India was only $450 a year. By the time you get to 2023, India over this time frame had more than doubled its emissions while increasing the per capita income by a factor of 5. And so basically, energy consumption is going to be an outcome of increased per capita income, increased standard of living, while developing nations increase their GDP. But that rise out of poverty is something that all countries that are in situations like India and China are going to want to do, and there's really no justification for us not to allow them to improve their economy. But it would be nice if we could advance their energy systems so it's not such significant emitters as is the use of coal. And China predominantly gets their energy from coal, as does India. So that's something that, a lot of people in the oil and gas industry said, well, if we can move them over to natural gas for electricity instead of coal, that would be a significant improvement, which that switch from coal to natural gas is a predominant reason why the U.S. is falling in emissions, which we've talked about. Okay, so we stick with this chart just for a little bit more. Let's see what the actual pledges were. So here, 2005 is a reference year for the United States. That's our target. Our target was to reduce our emissions by 26 to 28% by 2025 from our 2005 levels. And you can see we were pretty much on track. I've read some articles that said data's not all out yet, but since 2024, the U.S. has actually started to tick up again in their emissions. But if you look at this data set, which is the most complete data set that I could find, it looks like, well, it shows that the U.S. is declining its emissions. You look at Europe. Europe targeted a reduction of, I think it's a reduction of 40% from their 1990 levels. You can see they're on their way there. It doesn't look like they'll meet the target by 2030 of emissions, but they're also declining. 35% reduction since 1990. The U.S. has a 22% reduction since 2025 when we look at the 2023 numbers. But basically you see that we're both reducing emissions approximately on the same trend or the same slope. China is up 90% over the same time that the U.S. is down 22%. So you could argue that, well, China more than erased all of the emissions gains by the United States and Europe. And the question is, will they continue on that trend? And India is up 135% from 2005. So just India actually has erased the reductions, the reduction gains by the United States, for instance. So there's a lot of discussion to be had about how much economic pain would an advanced country be willing to take on when justifiably these developing countries are emitting more and more every day. Okay, so that's a little bit about what the emissions looks like for the top 4 emitters in the world, basically. Europe is not a country, it's a collection of countries, but it seems like an entity that that can be represented as one. And so the China is the biggest emitter in the world. The United States is second. Europe as a whole is third, and then India is fourth. And you can see the populations here. The United States is the smallest population of those groupings at 300 plus million. All of Europe is on the order of 500 million, so it's a little bit bigger than the United States. Okay, so let's look at some of the data from climate that's associated with these emissions. So, and this goes back 500,000 years, this data set. So this is looking at kind of the past history and looking at present day changes in the context of past history. Okay, so there's 3 charts here. The top chart is CO2 concentration in the atmosphere in parts per million from 0 to 400 parts per million. The middle chart in red curve is the temperature anomaly reference to pre-industrial levels in the world, plus or minus, well, plus 2, I guess, plus 3 degrees Fahrenheit down to minus 8 degrees Fahrenheit. And remember the COP21, the Paris Agreement goal is to keep the rise in temperature less than 2 degrees C out to 2100 from pre-industrial levels. So 2 degrees C is about a little bit over, almost 4 degrees Fahrenheit. Okay, then the bottom curve is sea level change, and this is in feet. And so we've got the reference state, 0 feet here is a reference state to the pre-industrial levels, and then it goes down as much as 400 feet. Okay, so first let's look at CO2 concentration. You can see it's cyclic, even without humans, because humans were not a major civilization until, organized with energy consumption, all that kind of stuff. We weren't really changing CO2 levels in the atmosphere or doing anything that would change CO2 levels in the atmosphere until after the last ice age. So the last ice age goes back about 10 or 20,000 years. We'll see a better curve in a minute. You can see when we're in an ice age, the CO2 concentration goes down. So this is when there's a lot of ice in the world. And then when we come out, the CO2 concentration goes up. And we have this cyclic nature of history. It's about every 100,000 years, there's a major cycle. Average global temperature seems to run with this cycle of CO2. A lot of questions are whether CO2 drives temperature or temperature drives CO2. But this shows there's a strong correlation between CO2 and temperature. And again, here, the last ice age and the Holocene, let's see. So this is, I think the Holocene is actually the end of the Pleistocene. So that's the beginning of it's the end of the last ice age. This is the rise in temperature coming out of that. And we're in an interglacial period right now, which is a higher temperature period. And you can see there's quite a bit of fluctuation. If we go back to CO2 concentration, so let's just look at this cyclic nature, but it goes from a little bit less than 200 parts per million to 300 parts per million is a kind of historical cap over the last 500,000 years, 500,000 years. But this little, what's called the hockey stick, shows that we've gone above 300 parts per million of CO2 in the atmosphere to 400 parts per million as of the date of this graph, which is about 10 years old. But the present day number for 2026 is 430. So we're actually, I lost my mouse here. We're actually about right up here right now. Okay, so that's where we are. We're out of bounds from historical records of CO2 over the last 500,000 years. If you go further back, you can see higher CO2 amounts. And so the worry is that you can see temperature has not risen as much as the CO2, and the worry is, though, people are worried about is the temperature will follow the CO2 if temperature is driven by CO2. So temperature can have an impact on people's lives and safety. If the temperatures get too hot, it can be hotter than humans can withstand. There are some places, very hot places, that are naturally hot in the world where temperature has gone up significantly. The other thing that people are really worried about is sea level rise. And you can see historical changes in sea level over the last 400,000 years are on the order of 400 feet. So it swings incredibly. When we're going into an ice age, water is bound up in ice caps, and so sea level goes down because the fresh water, or the water, is pulled out of the oceans and goes into ice. And then when things warm up and the ice melts, we come out of that, and there's a significant sea level rise. And you can see the sea level drop takes a long time to create the ice. The ice melt is much, much faster. And these signals correlate with the temperature signal, which correlates with the CO2 signal. Okay. 350 to 150,000 years ago is a lot messier, but you can see from about 120 or 130,000 years ago, there's a very prominent decline in temperature and a prominent decline in sea level, of a drop of almost 400 feet going into the ice age, the peak ice age, and then boom, we bounced out and sea level rose by 400 feet. Okay. And present day, we are just slightly above what this reference zero level is for pre-industrial levels. Okay. So I think a lot of that is said in here. Okay. So now here's a more detailed picture of sea level rise, which is very interesting. And this is actually scaled in meters. So instead of 400 feet, we have a scale of 150 meters. And this is starting out zero level as to the present day reference level. So the last glacial maximum is back here. Sea level was 120 meters below present day. You can see the locations where all these measurements were made. And these are basically geologic data that's used for this. And there's a fair amount of scatter, but you can see going from the glacial maxima, that's about 21,000 years ago. Really, things didn't start changing until about 15,000 years ago. And then from 15,000 years ago to about 7,000 years ago, we had more than 100 meters of sea level rise. It's a really incredible rate. At about 30 millimeters per year was the rate of rise. And then we hit a plateau, and we're on that plateau still. Okay. And so there's no question that significant sea level change is part of the natural cycle of the Earth's history. Okay. But this shows over a span of, let's see, from 15,000 to 8,000, let's say. So over 7,000 years, we had 120 meters of sea level rise. So pretty incredible. 30 millimeters a year, though, is a reference number you want to remember when we talk about looking at present day sea level rise in more detail. So here's some data from a published paper that includes, the references for the chart are Church and White and University of Colorado studies in the early 2000s. And what you see is a whole lot of scatter. There's uncertainty bars on here. But what they've done is they've put some curve fits on here that from 1870 to 1924, we were rising at about 0.8 millimeters per year. Then we jumped to 2 millimeters per year up until 1992, and now we're at 3 millimeters per year. We'll look at this curve again to see how the choices you make in curve fitting can impact what you would interpret things are. But it looks like, since the mid 1800s to the early 2000s, we've risen by about 200 millimeters in sea level rise. So 200 millimeters is 20 centimeters of sea level rise. Okay. Here is a projection from the IPCC, so the Intergovernmental Panel on Climate Change, which is part of the UN. And they've got different scenarios, which are listed here, RCP 2.6, RCP 4.5, and so on. And so from optimistic to pessimistic sea level rise projections based on what they think our energy consumption will be in CO2 emissions. But you can see going out to 2100, which is that target date from the Paris Agreement, there may be as much as 3.2 feet in the absolute worst case scenario to maybe something on, 3.2 feet or 1 meter. Let's talk meters since this chart's in meters. Or to as much as 20 centimeters. But we're already at the 20 centimeter level, right now. And so that's not very much additional change. And so so this would be kind of a net zero projection. This would be continuing emissions as we are today. Okay. So these are the projections. So a 1 meter increase could be a difficult situation for many coastal cities, because many coastal cities are within a meter or two of current sea level. Okay. And when that becomes a real problem is when you have storms, and so tides come in above sea level, and tide surges, which can be dangerous. Okay, so let's look just as for the sake of engineering practice and engineering methods. Let's look at curve fitting a little bit, because you can get in trouble when you make curve fitting. Now, I'm not going to be able to do this in a great amount of detail, but because I don't actually have the data set, but I pulled a few points from the curve, from this curve, and then did some curve fitting using Excel. So the question is past history a reliable indicator of future performance? That's something that people ask about the stock market all the time. Now, if we use Excel to put a curve fit on this data right here, and I pulled 4 data points here from the best trend I could get, the best fit to the curve that I got was a polynomial. Okay, and this is an automatic curve fitting capability that Excel has. So my R squared, which is a measure of good fit, perfect fit would be 1. My R squared is 0.9999. And what this shows is if we did this fit, if we were back in the early 1900s trying to do this fit, we could predict, oh my gosh, this would be horrible. Sea level is going to rise exponentially over the future decades. Okay, and so I'm partly showing this just not that the sea level paper that I showed you, they didn't do this, but I'm just saying this polynomial fit is a very dangerous thing to use for future projections. Okay, because it results in significant swings, and so if we add some more data, we'll see whether this is accurate or not. But before I talk about that, a more conservative way to look at projections is to use a linear fit. And so here's a linear fit, and you can see the linear fit isn't as good, but it's almost as good. And the linear fit is more conservative. So if you're doing engineering analysis and things, you don't want to be too outlandish in your predictions. Okay, and so linear fits are always probably the best, particularly if you're going to project significantly out into the future. Okay. Now, if we add in the additional data, you can see the polynomial fit ended up being a horrible prediction for future performance of sea level rise, but the linear fit actually is pretty good. And particularly, I've overwritten this chart here, but if you look out 5, 10, 15, 20 years, particularly out to 20 years, it's an excellent predictor of sea level rise. And I think this is approximately at the rate of, if you look at the equation here, y, which is sea level rise, equals the sea level rise per year, where x times x, which is year, minus the y-intercept. So we're predicting about 1.3, millimeters per year out to 1920. I didn't predict beyond that. And then it looks like actually there's a dip in sea level. But if you keep projecting that 1.4, I guess I averaged that up, 1.4 millimeters per year, that's good all the way out to 1990. Okay. And I would say that's an excellent fit. Now I'm biased to be a little bit more conservative about what's happening with sea level change. So I basically show a projection of a 1.4 millimeters per year that's accurate out to 1990. If we look at the previous case, they actually broke this into two pieces, which allowed them to get a higher increase rate of 2 millimeters per year for this segment from 1930 to 1990. My fit is much more conservative. Okay, but this is the same data set. Okay. But then in about, you could argue 1970 or in 1990, things seem to change, and now there's an excursion. And so that excursion, as interpreted by the paper I just showed you, is 3 millimeters per year. Okay. So we do appear to be at the 3 millimeters per year increase rate currently. But this shows a little bit about how you might use curve fitting to predict future performance of either natural systems or built systems. And in general, I mean, this is obviously not an in-depth discussion of this, but in general, I think the conservative approach is a much better approach. It won't get you in trouble. You can see this polynomial fit. Really, polynomial fits are really best for interpolating. If you have a few data points, you don't know what's happening in between, you might use a polynomial fit. But when you have things raised to the third power, you can get pretty big excursions as you go far out in time. So polynomial fits are not good engineering practice in general. Okay, so increased CO2 in the atmosphere is causing the hypothesis is that causes increase in world global mean temperature, and then that drives sea level change. That's the main climate change concern and story. And the consensus of the scientific geoscience and geophysical community is that is the true story. That's what the best interpretation is. That CO2 is driving this temperature change. And no question, nobody questions whether temperature change drives sea level change. Now, there's a lot of debate about the degree to which, basically the future projections and how fast are things changing and how bad will it be for human society. And that's when you hear people complain about climate alarmism. And that means, some leaders in the UN have said the Earth will be uninhabitable. 10 years ago, they said it would be uninhabitable by 2025. Now, some people are saying uninhabitable 10 years in the future. I think those clearly are predictions that are extremist. But on the same side, there's other people that say, well, we shouldn't worry about it at all and just go about our daily lives with emitting as much CO2 as we can. It's not a bad thing. I think that's not a good approach either. So we need to come to some sort of group consensus, including people on the environmental side and people on the fossil fuel side, that addresses both environmental impact but also human development and human standard of living, which that standard of living and human development requires a lot of energy. And where are we going to get the energy if we don't use our fossil fuels? Okay, so if we look back at how human society has transitioned from one fuel to another. We've already talked about this a little bit, but this is a different display of this. We've got wind is blue here, coal is black, oil is orange, natural gas is kind of this weird green color, hydropower is yellow, nuclear is the gray, and then down here we've got solar and wind down here, kind of at the noise level. But what this shows is the percent of the energy mix held by each one of these fuels or energy sources from 1800 to 2020. And you can see we were predominantly a wood burning world until about 1900, at which point, so on this historical thing, in order to transition from wood to coal, so coal was just starting back in 1800, it took 100 years to transition from wood to coal as the dominant part of our energy mix. And then coal reigned supreme, so to speak, for about 65 years. Okay. And then in about 65 years, oil came in. This is in the 1960s that oil finally exceeded the share of coal in the world energy mix. And you can see oil has maintained its leadership, although coal is oil has reduced its amount, and coal is basically coming back up a little bit as far as the world goes, to almost be the same share as coal. I mean, coal is almost the same share as oil in the world mix. Natural gas, so you can see, has been very steadily increasing since the 1940s. And I would project, in a linear projection, you may notice that the oil market share or energy mix share is declining. It looks to me like natural gas will probably exceed it in maybe in the 2030s. And so I would guess that's probably the next dominant energy form is natural gas. Okay, so next energy transition would be oil to natural gas. So what will that mean? Well, and this is something that I said previously as well. This is the energy mix chart over here, which gives the impression that we basically have stopped using wood, we're using less coal, we're using less oil. But this chart on the other side, and we looked at that Our World in Data chart. This is a different chart that I made myself, but this shows the actual consumption in terawatt hours, which is a horrible unit. I apologize for that. Would have been exajoules or quads would have been better, but in terawatt hours per year. And so what you see on this chart is the world uses about 80% more wood since we so-called replaced it with coal in 1900. Okay, so here's the crossover in energy mix percentage, but wood has increased in actual consumption. Then when coal and oil crossed, so oil exceeded coal in the percent of the energy mix, we still are rapidly increasing our consumption of coal, and we are still rapidly increasing our consumption of oil, even though its market share has been declining. So this chart is a little bit misleading. It implies reduction in consumption, whereas actually in all of these cases, the wood to the coal to the oil, it's all continuously increasing since those energy sources came on the scene. And here you can see natural gas is rising the fastest of all. If you look down here, for solar, you can see solar is coming up. This is wind that's coming up here. So you can see those are significantly lower, even lower than wood. So hydropower, though, has basically reached the level of wood. This is by 2020. So lessons from the past are that energy transitions are basically adding new forms of energy excuse me, to meet increasing demand while keeping all other forms of energy at their past level, or even continuing to increase the consumption of other forms of energy. So let's see what some leaders of U.S. economic sector have to say about energy transition. And so you can see that when we looked at some charts of data, wind and solar are growing at a rapid rate, but there's still significantly less contribution to our energy mix than oil and gas. But some have talked about whether we need oil and gas anymore since wind and solar are being so successful. And these are comments from 2022. So Jamie Dimon basically the CEO of JP Morgan, who has a very influential opinion in the economy, basically had testimony to Congress, and he said in 2022, we need proper investment in the oil and gas complex. Investing in oil and gas complex is good for reducing CO2. Basically said, if we don't use oil and gas, then many countries actually end up having to revert to coal, which is a bigger emitter. And so it's in our best interest to keep oil and gas healthy and contributing to our energy mix. The CEO of Chevron, Jamie Dimon's not an oil company person. He's a corporate America representative. The CEO of Chevron has clearly got some bias towards the oil and gas business, being a major company in the oil and gas business. But what he said really rings true, at least to me. So he said in an interview in Forbes that the reality is fossil fuel is what runs the world today. And I've told you, the world is 80% fossil fuels. It's going to run the world tomorrow, and 5 years from now, and 10 years from now, and 20 years from now. So he's basically saying, if you realistically look at the energy mix of the world, which includes the United States, fossil fuels are an integral part of it. And so in the United States, that's not surprising, because the U.S. is more or less, shows less corporate concern, I guess, about climate change and the need to change. But there's also a quote from a European oil company. Now, again, this is an oil company, but Total is very, very involved in low emissions energy resources. And so the CEO of Total, which is a French company, said, today our society requires oil and gas. Our energy, it is 80% of fossil fuels. There is no way to think that overnight we can just eliminate all that and rely only on 10% of low carbon energy. It will take decades to build a new system. So he's basically saying that any transition will take decades to happen. And, like I showed, past transitions really just showed an increase in contribution from a newer technology energy source. It doesn't erase the usage of old energy sources. But anyway, so Total, which is in Europe, and really in order to be in a favored status for a corporation in Europe, you have to be promoting net zero type activities. Even there, this oil company executive saying, it's just an incredible task, a very difficult task for us to move to a new energy system. Okay, so I've been kind of implying that we're going to continue to use oil and gas. Well, I have been implying, and I believe that we'll continue to use oil and gas as a significant portion of our energy mix, continuing for many decades out into the future. And as I said, it's just really the dominant form right now. No questions asked. So in the absence of an energy transition where we reduce oil and gas, is there an answer to responding to growing emissions? Because it does seem like a real concern. Like I said, the legitimate debate, I think, over CO2 emissions is how significant are the climate changes and how significant is the impact of those climate change, or how significant are the impacts of those climate changes on society. So in the absence of emissions reduction, we can do emissions mitigation, and that's called carbon capture and storage. And that's the theme of our labs that we're doing, homework and labs that we're doing right now. And so here we have basically first part of carbon capture and storage is the capture part. And so we capture CO2 at concentrated combustion sources like power plants. Okay, so here's imagine this is a coal-fired power station. It could also be a manufacturing facility, but at a coal-fired power station, we're basically going to capture the CO2 before it's emitted out of the smokestacks. Okay, and they call them smokestacks, but really all the clouds you see coming out of the smokestacks at a power plant are almost entirely water vapor. So Carbon capture is a chemical process. Basically, there are chemicals that react with the flue gases coming from the coal combustion chamber. And in order to drive that chemical process, it adds about a 30% energy cost to the power plant. Okay. And so that means in order to capture CO2, we have to use 30% more energy to generate the same amount of electricity. And so that will be a cost to consumers. Once you've captured it, then you send it out to the field where you would basically pull out other undesirable components like sulfur from the CO2 stream that you pulled through your carbon and capture. And then you would drill wells. Petroleum engineers would drill wells in order to store that CO2 in the subsurface. And so we need to find things like deep saline aquifers that have good geology. And good geology means high porosity and permeability. I said injectability here. And also we need to have an effective confining unit. So let's say we're injecting into this zone down here. This orange layer would be potentially a good shale that would have low permeability. That would be a barrier or a seal to keep this injected CO2 under the ground. So if we're going to inject the CO2 into the ground, we want to make sure it doesn't leak out later. Okay. So that is carbon capture and storage. So we need pipelines, we need wells, we need to do additional chemical processes at the power plant. And we need good geology. I say here deep saline aquifers. Another option for injection is depleted oil fields. Okay. Notice, well, I didn't write it up here, but there's another thing called carbon capture utilization and storage. So utilization means making products out of the CO2. And so, or doing things that are productive with the CO2. So one of the components of carbon utilization that's currently being used, and it does make money, so it's economically viable, is to inject that CO2 into active oil fields, not depleted oil fields, but active oil fields, in order to produce low carbon oil. And this would be an enhanced oil recovery method in the oil business. And so here we pipe this CO2 over here to the oil field, and then we pump it down. Well, actually, they show it's coming from here. So here it's coming through, and we pump it over here into an active oil field. We inject the CO2. It pushes the oil out. It also combines with the oil to modify the oil properties to make it improve its viscosity so it can be produced more easily. And in that process, some of the CO2 cycles back to the surface with the oil, but a lot of the CO2 stays sequestered, is what we call it, in the subsurface reservoir. Okay. So, but you're producing more oil, so you're getting an income stream to pay for your CO2 injection by the additional oil that's produced. And so that's why I call this low carbon oil, because prior to the combustion of this newly produced oil, you're storing some CO2 from past combustion. So you're actually decreasing the CO2 budget in the atmosphere, or the CO2 level in the atmosphere, prior to combusting the newly produced oil. So that would be a low carbon oil. Or if you really can inject huge amounts of CO2, it could be negative carbon oil. But I don't think the CO2 that's trapped actually, well, I know it's not. The CO2 that's trapped is not greater than the new emissions that would come from the produced oil. But it does reduce the overall effect. Finally, in utilization, we can create products. That's a very challenging component because there's so much CO2 that's being produced by burning fossil fuels that it's hard to come up with ideas to have products that will use it all up. But things like, well, you think about, and they're not actually getting their CO2 for Coca-Cola from this, but Coca-Cola has CO2 in it for the carbonation. Any soft drink has CO2 in it. So that's one potential product. Some of the products I've heard of include making bricks, actually combining the CO2 with some other elements. So you can imagine you take CO2 and combine it with calcium to make calcium carbonate. That's calcite. That's a solid that could be used for something. There's other carbonate types minerals that you could use to make solid things like bricks, and there are other applications as well. Okay, so that would be carbon capture and storage. The CCS is just strictly storing things. Carbon capture utilization and storage would include enhanced oil recovery operations and making products from the CO2. Okay. Now there's another technology. This is capturing the CO2 as we create it at power plants or other concentrated sources, and then injecting it in the ground. There's another thing which is basically to address legacy emissions, so emissions that are already in the atmosphere, and that's called DAC, which is direct air capture. Okay, and so this is the visualization of a facility in West Texas that Oxy, well, at the time was going to build. I think they've actually built it now. And so they have these huge fans which pull in air just from the atmosphere, and they run it through various facilities in order to pull the CO2 out of the atmosphere directly. And so we are at 430 parts per million carbon dioxide in the atmosphere. If we could pull enough out to reduce that amount, that would be incredibly successful. Now, the reality of that, though, is if we look at a concentrated CO2 emission like a power plant, the CO2 is very concentrated in the flue gas. I can't tell you what the ppm is, but it's very concentrated, much, much higher than the 400 parts per million in the atmosphere. So the lower the concentration of CO2 in the gas that you're processing, the harder it is to get it out, and the more total gas that you have to process in order to get it out. So this is a challenging technology to be successful, but the idea is, well, and it has a cost because it takes energy. Okay, so the idea would be, well, let's get a non-emitting energy like wind and solar to run a plant like this for the power, and then you would be removing CO2 from the atmosphere without creating any additional CO2 by your power source. So, for instance, you wouldn't run a coal-fired power plant in order to power your direct air capture, because you might not end up having a net reduction in CO2 in the atmosphere. But anyway, this is a technology that there's a lot of debate about whether it'll work, but it's an idea of actually what's called a net negative type of operation, where we're basically it's not preventing CO2 emissions, it's actually removing CO2 from the atmosphere. So that's where we get the negative. It's a negative contribution to the parts per million of CO2 in the atmosphere. Okay, so just in summary then, we've talked a fair amount about energy and standard of living are closely linked. Energy consumption is increasing. That's not going to stop, not just for basic standard of living things, but the technology like AI is increasing the total demand for energy for computer farms and stuff like that. So server farms. The largest countries in the world have significant energy deficiency in their consumption compared to the United States, which correlates with low standard of living. So they're going to want to increase their consumption of energy in order to catch up to the rest of the world for standard of living. That represents a huge increase in emissions. Most of the world's energy to make this advancement in people's standard of living comes from fossil fuels. So CO2 emitted due to energy consumption is going to be increasing as less advanced economies grow and lift their people out of energy poverty. And so we're going to see currently expanding our energy resources to meet that demand. It doesn't seem that we're going to have any sort of transition that replaces fossil fuel. Seems, given the demands on the energy system and the current technologies we have, we're not going to be transitioning. We're just going to be adding renewables to the mix and maybe not reducing fossil fuel consumption very much.